Hello, welcome back to our discussion on turbulence modeling. And today we want to continue our discussion on scaling with respect to the estimating the minimum DNS mesh size. So in the last video, we talked about how the Kolmogorov scale is related to the DNS scale, okay, or rather how it's related to near wall units. So in terms of near wall units, the Kolmogorov scale is about two like near wall units. So usually your smallest mesh size is about 10 to 20 times less than the Kolmogorov scale. So that's just something, a good rule of thumb to take note of, because you don't want to go through all these complex calculations. You just take your Kolmogorov scale, divide by 10 or 20, and you get your smallest DNS mesh size. Okay. So that's one of the things. And of course, if you want to carry this on over to mixed convection, especially those with low Richardson number meaning to say the flow is dominated by forced convection rather than natural convection, then this rule should still apply. Alright, so yeah, the more difficult case to deal with is actually natural convection. So you can also kind of use the same rule. You take your Kolmogorov or bachelor scales, all right. You take your Kolmogorov or bachelor scales and you divide by 10, and that should give you the smallest mesh size you need for either forced or natural convection. Now, for natural convection, how can we go about to prove this? Because if you want to do this near wall modeling, you see that the wall coordinates for these dimensionless quantities near the wall, they are done slightly differently. So instead of u tau, you use uq, which is like the heat flux, the velocity based on the heat flux, and that's very important in natural convection. So if you want to get dimensionless quantities, you want to get the scales near the wall, you got to understand the scaling units near the wall for natural convection. So this is, all of these were based on wall functions. So we got our dimensionless quantities, u plus and y plus, they were from wall functions. Likewise, uq it helps us to derive get coordinates for the wall functions as well. So let's do this estimate first. And let's see where we go with this. All right, uq equals to g beta alpha q wall over rho cp. All right, and it turns out that if you get your Nusselt numbers, or your wall convection heat transfer coefficients, you can calculate Q wall and you can plug it in to theoretically get this y star value. Now that's fine. You should know your alpha as well, so that's fine. It's a thermal diffusivity. Now for velocity length scales, it's slightly more challenging because you have two boundary layers you're talking about here. Whenever you deal with heat transfer, one is the thermal boundary layer, which is determined by this y star. The other is to deal with the velocity boundary layer and velocity length scale. So nearest to the wall, this y1 star star is used, and that's a bit more complicated. You see there's y in there, there's alpha, and there's a u tau, which is this friction velocity, and uq. So if you were to substitute this correlation in, you just get y star uq over u tau. So that's the important thing. Problem is this: estimating u tau near the wall is a pain. The correlations near the wall are sparse, if anything. Most people don't really care much for wall shear stress in natural convection applications. So people care about wall shear stress in, let's say, an aeroplane, airfoil, or pipe, where you want to estimate skin friction. For natural convection, it's not so much a concern. So the correlations are very, very few. So again, we can use our ballpark estimate, 10 times than the smallest. You take your bachelor scale and your Kolmogorov scale, you calculate it and you scale it down by 10 times. And okay, so that is the ballpark estimate. If you really want to be conservative, then I would say there is a lower bound estimate where we try and convert natural convection, and we think of it as sort of a mixed convection or a forced convection problem. This is a bit of cheating here. So method 1, we pretend the situation is a mixed convection and set Richardson number to 0.1. Remember, Richardson number is actually the ratio of the Grashof number over the Reynolds number square. And if we get a Richardson number low enough, that means that, you know, forced convection dominates. So I would say that the Reynolds number equivalent is just basically 10 times a square root of 10 times the Grashof number. And if you know, we know Reynolds number is actually u times some length scale over nu. So the relevant velocity here is called this buoyancy velocity. Okay, we can call this buoyancy velocity based on that. Okay, and we do this kind of calculation for this buoyancy velocity. After that, we use this buoyancy velocity or this Reynolds number equivalent, so to speak, substitute for this Reynolds number for natural convection. We push it in, we plug it into, you know, one of those standard wall friction coefficient estimates. So we assume, what we are assuming is basically that your buoyancy velocity is the free stream velocity equivalent. Okay, so if you have a flat plate flow, okay, flat, that's not very flat, yeah, that's better. So if you have a flat plate flow, you have your boundary layer forming, and then you have U infinity. We say this U infinity, we use U buoyancy here. U buoyancy here, and we try and estimate the skin friction coefficient. That's all we are doing with these methods. So this is a very, very, very conservative estimate because we are getting the U buoyancy very, very high, because we assume that, you know, the forces of forced convection are 10 times the Grashof number. Okay, so we assume that there is a fictional flow there, a fictional forced flow. Okay, fictional forced flow. All right, so yeah, excuse me. Yeah, so we have let's say, okay, so we have a wall convection case, right? A wall convection case, and we have some Grashof number. Okay, so what we are doing when the physical model, when we do this, is to have a Reynolds number, a force flow that's going along with this Grashof number, and I say this RE square is about 10 times, excuse me, yeah, it's about 10 times the Grashof number. Okay, let me shift this whole thing there. So I cover this. Okay, 10 times the Grashof number. Okay, so that's the idea behind it. Or of course we can use this buoyancy velocity. This is the second method which I was talking about just now. Pretend the free stream velocity is this buoyancy velocity and estimate the skin friction coefficient. So this one is assuming we put in extra flow into the system. So this is a very, very stringent way of doing things. Put in 10 times the Grashof number as the force flow, and use that to calculate skin friction coefficient, or just pretend that the buoyancy velocity is what we use to estimate the skin friction coefficient. So let's do an example to see whether these methods are valid, whether this ballpark estimate is valid, this lower bound estimate is valid, and whether this, the ultimate scale of comparison is to have these wall units show up. Of course, this is a bit more of a work to do. So let's have a square cavity where we have, a square cavity where you have your left side is hot, you have a hot temperature, the right side you have a cold temperature, and you can see the direction of the arrows will be the equivalent direction of velocity. Near the hot wall, the fluid will rise because of natural convection. Near the cold wall, the fluid will sink because of natural convection as well. So how can we estimate all these parameters to get our smallest length scale? Okay, you just I'll bring you along, and we can estimate it to get like this. So what I did for this is we have a square cavity. Actually, I took a look at Ampofos, and I'm not sure how to pronounce his name. I'm looking at this guy's paper. Okay, looking at this guy's paper, and okay, I should insert citation somewhere. Ampofo. All right, this guy. Experimental benchmark data for turbulent natural convection in a square cavity filled with air. So this is actually let's put this here. Okay, this is very important. It's very important because yeah, it's experimental data, so we have something concrete to compare to. So we have our hot side temperature to be 50 degrees C, cold side temperature to be 10 degrees C, and the cavity is actually 0.75 wide, 0.75 times high, or 0.75 meters high, and 1.5 meters deep. So this is not a 2D problem, this is actually like a 3D problem. But they try to make the cavity, the depth of the cavity big enough so that it essentially behaves like a 2D problem. But in actual fact, of course, it's 3D. Okay, so what are the Rayleigh numbers? The Rayleigh numbers are 1.58 times 10 to the 9th, and it's calculated like so. Is G times beta, which is the expansivity coefficient, T hot minus T cold, H cubed over nu squared, times the Prandtl number, of course. This is actually the Graw number. H is actually 0.75, which is the height of the square cavity, or the length of the square cavity, just one side of the square. Prandtl number, and it's not turbulent. Prandtl number is 0.71, and from these you can see your Kolmogorov scales. They are basically 1 to the 4th power of Prandtl number square over the Nusselt number minus 1 times the Rayleigh number. So the Rayleigh number is very important. We just have it here, so you can just plug it and play. Prandtl number we can also plug in, so we can see that estimating Kolmogorov scales are pretty straightforward. And now you want to estimate the Kolmogorov scale. We can actually use this scaling relation. Nusselt number is actually, it scales with 1 over 3, actually Rayleigh number to the 1 over 3rd power. The true correlation is this. I mean, it's I think 0.15 times Rayleigh number to the 1/3. Okay, this is for your, of course, the Bénard convection kind of thing, but I'm just leaving this thing out. I'm leaving this out so as to get a very quick estimate, so to see whether you can cut corners in that sense. So of course you want to cut corners because you want a very fast estimate. So this is the fastest way to get your Kolmogorov scale. So I substitute Nusselt number equals to Rayleigh number cube root into this correlation here. Of course, we realize that this cube root of the Rayleigh number is actually much bigger than 1, so I just get rid of the 1 over here. Because if you cube root this will be about 100, so really no point to have this minus 1 over here. So I'll just combine these together to get the Rayleigh number to the 4 over 3rd power. So it's Rayleigh number cube root times the Rayleigh number, you get this number. Then the Kolmogorov scale ratio becomes 0.0007 to 3 blah blah blah. And if h equals to 0.75, we have the Kolmogorov scale being about 0.5 millimeters. And what about the Bachelor scale? The Bachelor scale, we just take the Kolmogorov scale divided by the square root of the Prandtl number. That will give you about 0.6 millimeters. So of these, the Kolmogorov scale is smaller, and we can say our minimum mesh size is about 1/10, 1 over 10 of the Kolmogorov or Bachelor scale, whichever is smaller. And then we say our minimum mesh size is 0.05 millimeters, normal to the wall. So what do I mean? It's if I have cavity here, if I have this cavity here, this cavity here, I say this is the wall normal, and I'll say, okay, the spacing here of my mesh should be how much? 0.5 millimeter. Okay, so this is 0.5 millimeter. So that's the rough scaling we are talking about. Rough scale of the nearest wall cell. And so we have this wall normal scale being about 0.05 mm. And let's think about let's use our lower bound estimate again. So this was this is our ballpark figure based on this 10 times smaller than the Kolmogorov or Bachelor scales. Very, very easy to use, very, very fast. Now let's use our lower bound estimate, and that's actually a little more grounded based on correlations. So this is somewhat conservative, especially this method 1. Pretend the situation is a mixed convection, and we force 10 times the Reynolds number in there. So 10 times the Grashof number worth of flow, and we take that to estimate our Reynolds number. Okay, or we assume that the U buoyancy is characterized by the square root of the Grashof number. That will be our what will that be? That will be our free stream velocity, and we use a skin friction coefficient correlation to try and estimate the wall shear stress and the wall units. So remember we have these two methods, and I'm going to use this Schultz-Grenell correlation, where CFX equals to 0.37 times the log to the base 10. So this one's really the base 10 times the Reynolds number, and then you take the whole power to minus 2.584. So for this, very simple, we just substitute the square root of the Grashof number, or square root of 10 times the Grashof number, as this Reynolds number here. So I'm just going to plug and play. That's very simple, based on our ballpark estimates. And remember, we derived in the last video, or the last few videos, where U tau is actually equals to U mean times half, or the square root of this friction, square root of half the friction coefficient. Okay, so, and if we take that the length scale, the length scale is h, which is the height of the square cavity for both sides, then I'll say Re tau equals to Re mean. Okay, I won't say Re tau equals Re mean. I multiply both sides by h over nu, then we can get it in terms of Reynolds number. And then we substitute to get our friction Reynolds number. Re mean will be either 10 times the Grashof number, square root of 10 times the Grashof number, or just square root of the Grashof number, depending how conservative you want to be. So the first one, of course, we assume that it's a mixed convection, but with extra, extra force flow in there. So there's a very, very much our lowest bound. There is no scale that's going to go smaller than this. Okay, and this one is another way to estimate our ballpark figure. All right. So how do we estimate this? Again, we have our Rayleigh number, which is 1.58 times 10 to the 9th power. Again, I use a very skimpy method. Not skimpy method, but that's not the word to use. I use a very fast method. Try to cut corners again, make a shortcut. I would say that the Prandtl number is on the order of magnitude of 1, so that the order of magnitude of the Rayleigh number is actually the order of magnitude of the Grashof number. So what I do is just that I take this Rayleigh number, because the Prandtl number is so close to 1, I just use the Rayleigh number and substitute into these places where I would substitute the Grashof number. If you want to be rigorous, sure, but it'll just take longer. So I'm trying to take shortcuts to make it faster. So I substituted these in, and basically I get from these correlations. I mean, the first one, if you want to be ultra conservative, then I'll get the Reynolds number, okay, the friction Reynolds number of about 6588. So that's quite a lot. Over here, I have a Reynolds friction Reynolds number of 2380. If I just take the Reynolds number to be the square root of the Grashof number, or in this case, square root of the Rayleigh number, which is about the same. Okay, so looks like the friction Reynolds number is quite high. So this is very conservative anyhow. Okay, so I'll stop for now. Because it's 20 minutes. I'll continue in the next video. Thanks for watching.